today we have the pleasure and honor of hosting our speaker, Professor Michel Marcus from Vanderbilt University, to talk about, in my opinion, a very important and unexplored yet topic of impact of pollution in the water delivery system on households, and especially on small children or children. And this has a great potential to be replicated in other countries. And in an early discussion that we had with Michel, we realized, or we understood, that there is not too much research and knowledge and information about lead pipes to deliver water in many countries. So we look forward for listening to what Michel will tell us. So Michel, or Professor Marcus, is an associate professor, associate professor in the Department of Economics at Vanderbilt University, and she is also an associate researcher in the National Bureau of Economic Research, an organization that I also tried to join, but given my age, they did not accept me. So her research focuses mainly on, or broadly, on determinants of child health and well-being, with particular focus on environmental exposure and the effectiveness of different types of regulations. Her recent research focuses on quantifying the direct health impact of important sources of pollution, such as leaking underground storage tanks of probably gasoline, on lead service lines, and drinking water contamination. So this is by itself a great area of research, and we are ready to hear and learn from Professor Marcus. The floor is yours, Michel.
Great, thank you so much. And thank you everyone for being here. I'm just super happy to have been invited to this workshop. I'm going to go ahead and try and share my slides here. Hopefully we can get the right ones going. Can you see these okay?
Very well.
Okay, great. Make sure they advance. Wonderful. Okay, so I'm going to talk today a little bit about lead service lines and their impact on child blood lead levels and property values. So this is ongoing work. If you have comments and suggestions, I'd love to hear your feedback. So please don't hesitate to reach out either during this meeting or afterwards. I'd love to hear from you. So let's see. There we go. So the EPA, the CDC, the WHO all agree that for children, there's no level of lead exposure that's considered to be safe. And in economics, we have actually a pretty broad literature that has documented the negative short-run and long-run consequences of exposure to lead. So in the short run, lead reduces fertility and health at birth. In the medium to long run, lead also reduces cognitive function, test scores, human capital, earnings. It impacts criminal activity, behavioral problems, school suspensions, just to name a few. And so basically we know lead is really, really bad. Despite the fact that we know this from a large literature, In the US and in many countries, we still have millions of lead service lines that deliver drinking water to homes. In the US, the EPA just released a new report that's tried to estimate the amount of lead service lines in the country, and their estimates are about 9.2 million lead service lines. I tried to find some information on the amount of lead used in drinking water systems in Africa, and I must say it's not very well documented. I did find one study that found in 3 West African countries, 82% of the tested rural water systems contained lead. So that suggests that this is still a problem, and we would love to know more about how big of a problem it is. In the EU, estimates are around 120 million people are exposed through lead service lines, and in the US, the estimate is about 22 million people exposed through lead service lines. And especially in the US, we have this additional problem that we have more exposure to lead in disadvantaged communities. And so there's this equity issue that is really important. And before I go on, I just want to make sure we all have in our heads the idea of what I'm talking about when I say lead service line. So if you think about a drinking water system that delivers piped water to people's homes, the water main typically runs under the street. So in this diagram, there's a water main, and then the service line connects this water main to each individual house. And there's usually a publicly owned portion of the service line and a private owned portion. So that's designated by the property line. And so that will just be important to know as we go through the talk. So all of these issues with lead service lines really came to light after the US, at least in the US, when we had a few water crises. So in Flint, Michigan, in Washington, D.C., and in Newark, New Jersey, they had episodes of really elevated lead exposure that highlighted the risk of having all of these old lead service lines still buried underground. And so it sparked a lot of debate in the country and led to a few important policy responses. The most recent response has been the US EPA's new changes to how we regulate lead in drinking water systems, and those became effective at the end of last year. They actually require that throughout the entire country, we start replacing all of the lead service lines that exist, and the goal is to replace all of those 9.2 million in the next 10 years, which is a really ambitious project, and it's going to be very expensive, quite a bit more expensive than the $26 billion that's been dedicated to these replacements through the Infrastructure Investment and Jobs Act. So we'll need a lot more money, and given that we're spending billions of dollars on replacing these lead service lines, we actually would like to know what the effect of that investment will be, but surprisingly, we know very little about the causal effects of replacing lead service lines, especially as compared to what we know about the remediation of other lead sources. So if you think about, there's really great work on the effects of Superfund cleanups, de-leading gasoline, lead paint remediation. These are all important sources of lead that we've worked to remediate in the past, few decades, and those have been quite effective, but we don't really know what's going to happen when we replace these lead service lines. And you might think that that's obvious, but it's actually not obvious, and that's because these old pipes over time have built up mineral scale inside of the pipes that prevents lead from leaching into drinking water. So that scale actually could be protecting much of our drinking water as it is, and so maybe replacing these lines won't have much of an effect, or maybe that scale is not really present enough. And there's the additional problem of if we only replace half of the line, which is what they started to do in certain areas, disturbing the line can actually have that mineral scale fall off, and then we can actually have more lead in drinking water if we don't fully replace all the lines. So there's an ambiguous effect on child blood levels, and that's part of the reason why this research question that I'm going to look at is so important. And so I'm going to ask, how does a place-based policy of lead service line replacement impacts the households in the homes targeted by the policy. And so I'm going to look at child blood lead levels. I'll look at home prices. I'll look also at moving behavior and neighborhood demographics to see how these neighborhoods change after the program. And I'm going to do this in the context of a program in Providence, Rhode Island, where they spent over $55 million replacing around 10,000 public side lead service lines between 2007 and 2010. And the nice thing about this setting is that we have some plausibly exogenous rollout of where and when these replacements took place. And so I'm going to leverage strategies from Callaway and Santana that deal with this variation in treatment timing. So just to give you a quick outline here, I'm going to give you a little bit of background on lead, but also the setting in Rhode Island. I'll talk about the data and methods I use for the study, and then I'll go over the results, the main results on these 4 different outcomes. So a little bit of background to start. It's important to know that there's a lot of factors that influence how much lead there is in public drinking water. How much of the pipe system was actually built of lead is obviously crucial. How old the pipes are and the scale, that mineral scale inside the pipe, is all very important. There's also a lot of things that can change quickly over time, like the acidity of the water, the minerals present, temperature, and how long the water stays stagnant in the pipes. So if the water doesn't move for a long time, it will build up more lead. And so that makes measuring lead in drinking water a little bit tricky. How we regulate lead in drinking water is through the EPA's lead and copper rule, which requires that water systems sample a variety of homes. So they go into homes and sample the tap water, and they try to focus on homes that are most likely to have lead plumbing materials. And that's because most of the lead enters the drinking water when it passes through those lead service lines. When it leaves the treatment facility, it's usually clean. And we've had a lot of violations of that regulation in the past. About 1,000 systems violated our lead limits between 2013 and 2015. So this is something that happens fairly regularly. In Providence, Rhode Island, lead has consistently been a problem and a source of concern. So what I'm showing in this diagram is the 90th percentile of all those lead samples that are taken at homes over time. And when the 90th percentile crosses that 15 parts per billion, that red line, it triggers a violation of the lead maximum contaminant level. Anyway, it triggers a violation. And so for a long time, we were hovering just below that action level. And so because of the concern about lead, Providence commissioned a study to address their corrosion control. And the study suggested that they change the pH level of lead in drinking water. And so they did that in 2006. They changed the pH slightly to try to reduce lead in drinking water. Unfortunately, it had the opposite effect and accidentally increased lead. So you can see the first year in which there's this jump in lead levels is right after they changed the pH level, which is unfortunate. But crossing this threshold triggered a requirement for Providence to start replacing all of their lead service lines. So in 2007, they had to start this program. And you can see here I'm plotting the year of installation for service lines installed among older homes. And so not surprisingly, there's a huge jump in the number of lines installed starting in 2007, which is when the replacement program started. And it lasted for about 4 years. In 2010, a study came out that suggested partially replacing service lines might actually increase lead levels, and so they stopped the program at that point. So we're going to be looking at the program that occurred over these 4 years. Over these 4 years, they replaced about 10,000 lines, and they were required to offer to replace the private side. Remember, there's two portions of the lead service line. They replaced all the publicly owned portions, and they offered to replace private side portions, but it was at the homeowner's expense. And because of cost, which was about $3,800, most households did not agree to replace their side. Only less than 2% of households replaced the private side. So you can think of all of these replacements more or less as being just public side replacements. Okay, so that differs a little bit from the new law that's coming into place, which is going to focus on replacing both sides. So you can think of this as sort of an underestimate of what the new law will require. I'll sort of extrapolate my results to the fully replacing service lines at the end of the talk. Okay, great. I'll talk a little bit about the data that I use in this study. So fortunately, I have service line level data from Providence Water, which serves 60% of the residents in Rhode Island. You can see those service lines here in the figure on the right. The peach color is non-lead service lines. The reddish brown color is lines that are still made of lead as of 2017. And then the darkest color are lines that were replaced during this replacement program. And so you can see there's some clustering in where these replacements happened. And I'll talk about sort of who got replacements and who is exposed to lead in just a little bit. What's nice about the data I use in the study is I'm able to link these service lines to household level information about child blood lead levels. So Rhode Island has universal testing of child blood lead concentrations. They require that all children get tested twice before the age of 3, and then every year after that until age 6. And so I have all of those blood lead levels linked to these service lines. I also link these service lines to tax assessor home sales data and also some census data to try to think about neighborhoods. Okay, so we can linking all of these service lines to our census data, we can think a little bit more deeply about who is exposed to lead broadly and then who receives these replacements. So first, just looking at census block groups that either have some level of lead service lines and those that have none, we can see a pattern that's maybe not super surprising given other research, but block groups with lead tend to be more disadvantaged. So they have higher portions of households that are renting, more single family households, lower educated households, higher unemployment, less likely to be white, more likely to be non-white and Hispanic. And so this is a stylized fact that's been shown across a lot of different sources of pollution in the US, and but it's an important one to consider here, and the same pattern sort of holds. We can also look and see who received lead service line replacements. So columns 3 and 4 are block groups that didn't receive any replacements, and then block groups that received at least some replacements. And there's some small differences here. They're a little bit more balanced. In the paper, I go in the appendix and try and tease this out a bit more. But really the thing that stands out the most is these first 2 rows here. It turns out that the neighborhoods that received replacements had older housing stock and a higher density of lead service lines. And that's not really surprising if we think that the regulators were trying to be efficient in replacing these lead service lines. Once you dig up one part of the street, you might as well dig up the whole street. And so it's not really surprising that they targeted neighborhoods that were likely to have a lot of these lead service lines. Okay, so that's sort of who received these lines. We can also link information about the age of houses. So older homes are more likely to have lead service lines. They stopped installing lead service lines in 1937 about. and we can see that blood lead concentrations for children in older homes are much higher than blood lead concentrations for children in newer homes. Okay, so this is just showing averages for 5-year home age bins, and kids in older homes just have higher blood lead concentrations. Now that can be both because older homes have lead service lines, but also because older homes are more likely to have lead paint. So that's important to remember. There's multiple sources of lead in this setting. Drinking water is just one of many. Okay, so we can also look at lead tests, so of blood lead concentration for kids before and after they received lead service line replacements. So the same, this is for all children in the solid green line. The dark dashed green line is before they received replacements or at households that never received replacements. And then the lighter green line is at households that after they received replacements. And so reassuringly, we see this decrease in blood lead concentrations occurs in older homes, which makes sense. And we see a pretty sizable decrease here. And so we're gonna, in the next, few slides, test this a bit more formally using the rollout of replacements, but even this sort of descriptive evidence seems to suggest the good news that replacements reduce child blood lead levels. Okay, so let me talk a little bit about the methods that I'm going to use for this paper. So I'm going to leverage variation that comes from the staggered rollout of lead service line replacements at the household level. We have to assume then that replacements are exogenous to other household level changes that might impact blood lead concentrations. In this setting, we actually have the fortunate situation that the utility, the service utility, decided where and when to make lead service line replacements rather than the household asking for their home to be replaced. And the difference in that is that if we thought the household was initiating replacement, they might simultaneously be remediating lead paint, for example. And so it would be difficult to disentangle the reduction in blood lead concentrations from the water relative to lead paint. But because the utility is making these decisions, that's less of a concern. Now, households could still be doing other things, but because they were unwilling to take up private side lead service line replacements, it's probably unlikely they were also remediating lead paint, for example, which was much more costly. So replacing a lead service line was around $3,800, whereas replacing the paint for a 2,000 square foot home was more like $30,000. Okay, so it's unlikely they would, do one but not the other. Okay, so we're going to use this rollout, and our outcome is going to be average blood lead level for child I at age A and year Y. We'll have child and age fixed effects, and I'm going to estimate this with Callaway and Santana, which addresses the issue of heterogeneous treatment effects can bias estimates when you have staggered rollout. So you can check out that literature. It's great. I'm going to condition on year using their doubly robust estimator. Standard errors are going to be clustered at the child level with their multiplier bootstrap procedure. And then for our analysis on home sales, I'm going to use a very similar design, except this is going to be at the parcel year level. So we'll have parcel and year fixed effects, and I'm going to condition on a number of housing characteristics. So the parallel trends will be conditional on, total number of bedrooms, bathrooms, etc. And again, standard errors are going to be clustered at the parcel level. Okay, so let me just show you the results in mostly figures. I think I have 1 or 2 tables. This is the event study aggregation of those results on child blood lead levels. So the orange coefficients are looking at the pre-treatment periods, which are fairly flat. And then the blue coefficients are looking at what happens after children have a lead service line replacement. So you can see there is a general downward movement of these coefficients, and looking at the aggregated post-treatment effects, the effects are around 3.3 to 4 microgram per deciliter decline in blood lead concentrations. Okay, and so that's regardless of what type of aggregation method we use or whether we use the never or not yet control group, these effects are pretty stable and consistently significant across those different methods. In terms of the magnitude, that 0.4 microgram per deciliter decline is about 13% of the mean blood lead level. Or if you look at the gap between older and newer homes, it closes that gap by about 31%. We have other really great work looking at lead, and this is about twice as large as the estimated effect found from de-leading NASCAR races in this Hollingsworth and Reddick paper. And if we look and extrapolate these findings based on some other literature, we can, say that this 0.4 unit decline would lead to about 2 to 3% lower probability of being substantially below proficient in reading and math, and would also lower the probability of school suspension by about 2% and juvenile detention by about 23%. So that's based on these other literatures. So this is a sizable decline in blood lead concentrations in a country where we already have done a lot to reduce blood lead levels. It does close the racial gap in blood lead levels. So as I mentioned earlier, there's a lot of disparity in exposure. And so that black-white gap in blood lead levels goes down, but doesn't entirely go away. And so there's still more work to do there. And it begs the question of are we targeting the right homes? Are we actually getting the kids that were living in these homes to benefit from the policy? Okay, so let me talk a little bit about the effect on home sales. So I start by looking at the event study aggregation for the impact on the probability that a home is sold. So before it receives a lead service line replacement, there's pretty flat pre-trends and pretty flat after the program too. So there's really no significant effect of replacements on the probability that a home will sell. Okay, so they aren't more likely or less likely to sell homes, but conditional on selling your home, it looks like the log of home sales price goes up. So in the post period, these blue coefficients, there's an increase in home value of about 7 to 8%. And so that suggests that home buyers are valuing these replacements. Okay. So what happens to neighborhoods after these replacements come into place? It's not easy to answer this because we don't have super granular data on where people live. So we have to aggregate to a broader geographic unit, which isn't ideal when treatment happens at the household level. Nevertheless, this can be somewhat informative. And so in the paper, which I won't go into a ton of detail here, I do a little bit of exploration using census data to see what happens to rent and demographic information. And I find some evidence that rent increases. This is maybe not surprising because housing prices are increasing as well. And so that can be important. I also find mixed evidence on demographic changes here. It looks like neighborhoods that were more impacted by the lead service line program were becoming more white, again, paying higher rent, but maybe slightly lower income. And so that's a little bit confusing. And again, I think that's hindered by the fact that we're aggregating this to a broader geographic unit. Nevertheless, it suggests that there's some change happening. And so we might want to know whether households are moving after this program comes into place. Okay, so to look at moving, I want to know, was this place-based program that targeted certain households actually successful in reaching the households who lived there at the time, or did they move and not benefit from the program? With the blood lead data, I know where people are located when they get tested, and that helps me to know whether or not they've moved. And so looking at the probability that a child has moved, I see an increase in that probability after the lead service line is replaced. Okay, and that increase is about 8 to 9 percentage points. And this sample, because it's based on the blood lead testing data, includes both renters and homeowners. So it's the universe of children. Because there was no impact on the probability of home sale, which we saw a few slides ago, this suggests that this moving behavior is likely driven by renters. Okay, and that's important because renters are a really a more disadvantaged group in this setting. They're also quite a large group in this area, and they don't have the ability to necessarily bargain with their landlords to take on the cost of replacing service lines, right? And the landlord who doesn't live there has very little incentive to replace those service lines, especially if it's quite costly. And so these renters are an important and an understudied group. Okay, so we see increases in moving among renters. We can also ask the question, do the households that move, where do they go? Are they better off? Are they worse off? Is there no change? And we can partially answer that question by looking at the blood lead concentrations of those moving households. And so these moving households don't experience any improvement in blood lead levels afterwards. And so what that means is that they're likely moving to houses that have a similar level of lead exposure, whether that's both coming from the same sources or different sources. It's hard to say. We don't have as detailed data as we might like, but we can see that their blood lead levels are not going down. If anything, they're small positive, but statistically insignificant coefficients. Okay, so that suggests they're not really benefiting. Okay, so to sort of summarize the implications from this set of results, we see that lead service lines represent actually a significant source of lead exposure in children, and replacements do reduce child blood lead levels, which is great. It helps close disparities in lead exposure, but hasn't eliminated them yet. The reduction from these partial public lead service line replacements is about 0.4 micrograms per deciliter lower child blood lead levels, or about 13%. In the appendix of the paper, I'm able to extrapolate, so based on the length of the public and private portion of the line, how much lead we might expect to be reduced from fully replacing the public and private portion. And so those estimates are around 0.6 unit decline, which is around 22% of the mean, which is actually strikingly similar to the EPA's ballpark estimate of how much they think lead exposure is coming from drinking water, which is about 20% is what they guess. And so we're in the same ballpark there. The next important implication is that replacements increase home values. This suggests that home buyers value the public side replacements more than the cost to the utility. So that 7 to 8% increase in sales price is about $16,000 to $19,000, which is 3 to 4 times the average cost of public side replacements. Now, this could include, the amenity value of having your street dug up and repaved. That tends to look nicer. So it might not be increases coming only from the benefit of the lead replacement itself. Nevertheless, these are pretty sizable improvements in sales price. And then third, importantly, place-based policies might not benefit those living in the homes targeted by the policy. So in this context, renters faced higher rent, were more likely to move out after replacements, and when they moved, they experienced no change in their blood lead levels. So they really didn't benefit much from this policy. So it's important to note that residential mobility can undermine our remediation efforts, especially when those remediation efforts are incomplete. This can leave exposure gaps between disadvantaged and advantaged households in important ways that are things we should take into consideration when we design policy. So I'd like to take just a couple minutes to extrapolate the findings from this paper to the new lead and copper rule improvements that were just adopted at the end of last year. So this policy now requires fully replacing lead service lines rather than just partial replacements. So again, this is extrapolating our results is about a 0.6 unit decline in blood lead levels for those full replacements. And if we extrapolate even further based on research from others, which documents the link between lead concentration, IQ and earnings, this would lead to about $6,000 higher earnings for each replacement, which is pretty substantial. This policy also requires us to replace all 9.2 million lead service lines, regardless of how much lead is actually in the drinking water. So that's a big project. If we take the estimates from this paper seriously and extrapolate, this could lead to a $147 billion increase in home values. And importantly, it also mitigates the equity concerns from the endogenous moving behavior. If we replace all lead lines, then we're less concerned about people not benefiting from only replacing certain homes. But the problem is that, we haven't really dedicated enough funding to this endeavor. The IIJA funding is insufficient to cover the private side replacements. There's a lot of concern also about, who will pay for private side replacements and how we will encourage residents to actually take up this program. But it's really important, I think, to do so because it can help protect these disadvantaged groups that rent or are lower income and can't afford to replace their private side lead service lines. Yet we saw from this, summary statistics are disproportionately exposed to lead in this context. So I think there's more work to be done here, not only in the US setting, but also internationally. I think, just documenting where these service lines even exist is a really first order important task we have to do. Many of them were installed so long ago that there are no records of what these lines are made of, and they're underground, so they're really difficult to observe and catalog. So hopefully some of you on this call can help tackle some of that research agenda, and that's all I have on this topic for you today. I'd love to hear any questions or thoughts you have. Thanks so much.